Hi, my name is David, and today I will discuss my work for the 2022 American Control Conference. I did this work at the University of Nevada, Reno, in collaboration with a student at Indiana University, Bloomington. To start off, I will introduce an actuator known as the twisted string actuator. This is a transmission system that converts the rotation of a motor to linear contraction. The advantage is that you can get high output forces with low input torques. And also you can get high efficiencies. The strain is decent at 30 to 40%, and there are many robotic applications for this actuator. Some applications include exoskeletal devices, robotic grippers, robotic gloves, haptic interfaces, and many, many more. Besides the twisted string actuator, there are many other actuators out there to replace the traditionally used rigid robotic actuators. The goal is to develop an artificial muscle that can outperform natural muscle in all aspects. So far, there have been many different actuators that exceed the performance of natural muscle in at least one aspect, but so far there is still no functional equivalent to natural muscle. Next, I will introduce the field of soft robotics, which is a new robotics paradigm that enables new applications and capabilities by using these soft materials. This field has really exploded over the past 10 years, and it's been driven primarily by advanced material fabrication processes. There are many promising applications in environments such as medical and marine ones, and some examples of soft robots are shown on screen here. Given that there are many artificial muscles that we could use, the question arises of why would we like to use TSAs? The answer is that TSAs offer high stress output, high efficiency, and are simple to fabricate. In contrast, dielectric elastomer actuators require hundreds or thousands of volts to actuate, and their actuation forces tend to be very small. Soft fluidic actuators can be great for different applications, but the downside is they generally must be tethered because they require large pumps or compressors which are connected by pneumatic lines to the robot. In this work, we developed a physics-based kinematic model of a twisted string actuator-driven soft robotic manipulator. And each three parts of that sentence can be divided into three different research sections, which I'll go over in the coming slides. Next, I'll get into the fabrication for this manipulator. The manipulator was primarily composed of soft silicone, but its base was made out of rigid plastic. We used Dyneema strings, also known as ultra-high molecular weight polyethylene strings, because they have been used in previous works on TSAs. Our motors had no-load speeds of approximately 170 RPM, but their torques were fairly strong to enable a large bending range. I will also say that the particular size and speed of the motor is somewhat arbitrary, and that faster motors could be used if necessary depending on the application. We also used an angle sensor from Bosch to track the bending angle of the manipulator. Our proposed design consisted of three motors housed in the base of the robot, and then the twisted string actuation was realized by inserting these strings into hollow channels in the silicone that ran from the top of the robot to the base of the robot where the motors were housed. We also fabricated the robot such that the electronics were housed outside for ease of control and fabrication, but in future work this robot could certainly be modified such that the electronics are placed inside the robot, for example on printed circuit boards. Our robot was less than a kilogram in mass and approximately 300 millimeters tall. The silicone itself was 40 millimeters in diameter. Actuation was realized by contracting a TSA, which then contracted the silicone itself on one side. A video of the actuation is shown here. Other studies have also completed modeling for tendon-driven manipulators, but they tend to be based on solid mechanics or numerical methods. This does offer high accuracy, but the cost is very high computational complexity. In contrast, our model is derived from geometric relationships that enable an analytically invertible model, which can further lead to open loop control. We also have a low number of parameters that must be identified, yet we achieve high modeling accuracy. To start off, this diagram shows the parameters that are relevant to our model. Our input to the model is the motor shaft angle, and the output is the manipulator bending angle. The parameters that we must measure or solve for are the silicone dimensions and the TSA dimensions. Now that we've introduced those parameters, we can now derive the manipulator kinematics. We start by predicting the arc length L given the bending angle and radius of curvature. We also assume a uniform curvature radius, which is precedent in previous literature. Next, we assume that the center arc length L0 remains constant, as also done in previous literature. We also assume that the other TSAs that are not twisted have negligible impact on L and on the twisted TSA. Finally, we can generate equation 3 by doing substitutions. Now we will incorporate the model of the TSA itself. Equation 4 shown here has been well tested in previous work. It predicts the length of the TSA given the motor angle T of the motor. We must also assume that the length of the TSA equals the length of the silicone, but this is a reasonable assumption because of how our gripper was fabricated. Our final equation is shown here, which predicts the bending angle theta given the motor angle T. Next, we must also consider the variable radius of the TSA. Previous work has shown that the radius W will increase as the TSA length decreases. However, these two variables depend on each other, so we can't solve them simultaneously. Instead, we predict the current length of the TSA given the previous value of the TSA radius. Then we can predict the current value of the TSA radius given the current value of the motor angle and the previous value of the TSA radius. Now I'll get into the results for this robot. On the left figure, we have our motor angle input sequence, which consisted of 4 cycles of monotonically increasing and decreasing stepwise motor rotation inputs. In the center figure, we have the experimentally obtained and modeled results versus time, and you can see just from the middle figure that the results collected experimentally match the model with decent accuracy. On the right, we quantify our error by showing the error versus motor angle, and then we compare those values to the mean error magnitude, which happens to be slightly more than 1 degree. As given that our modeling error is slightly more than 1 degree, we can say that our modeling accuracy is high, especially given the fact that, as shown in figure B, our range of motion was approximately 60 degrees. Next, we can compare the modeling accuracy for the 3 different motors. Each motor was actuated by itself, but we apply the same model with the same parameters to the experimental data. As you can see, there are some unmodeled effects due to the softness of the silicone, but in general, we still achieve modeling errors less than 2 degrees. There is also a good amount of consistency between actuation cycles. Next, I'll get into the velocity characterization procedure. And what this consisted of is basically applying a step motor voltage input of 3.6 volts, but the particular value is rather arbitrary. Next, we wait 14 seconds so that the manipulator can reach its full range of bending. And then we apply another step voltage input such that the motor voltage decreases to 0 volts. After that, we apply a Savitsky-Golay filter, which smooths and differentiates the experimentally obtained data. For our velocity modeling, we used 3 different models, which offer different levels of complexity and accuracy. The complete model, shown first, considered both the variable radius of the TSA and the nonlinear TSA Jacobian. The conventional model considered a constant TSA radius, but also considered the nonlinear TSA Jacobian. Finally, the linearized model assumed a constant Jacobian and also a constant TSA radius. In general, we found that the average modeling error really depended on the range of actuation. So during some portions of the bending, the complete model was more accurate, whereas during other portions of the manipulator's bending, the conventional model was more accurate. And the specific reasons for this can be investigated in future work. But in short, we can summarize by saying that between a range of 3 and 32 degrees, the complete model had the least error. But then between the range of 0 to 58 degrees, which was the full actuation range, the conventional model had the least error. And so in future work, we should certainly study the physics of the TSA and the manipulator itself to uncover why these models offer different levels of accuracy at different ranges of motion. In this work, we developed a modeling strategy that shows low computational complexity, yet low modeling error. We show that using TSAs, we can achieve a high range of motion, showing that TSAs are effective for driving soft robots. In the future, we would like to study the multi-degree of freedom motion of this robot and develop multi-degree of freedom controllers. We would also like to improve our physics-based model by relying on less assumptions. Finally, we would like to attach an end effector to the soft manipulator as shown in this video. This concludes my presentation. Please feel free to reach out with any questions to my email shown on screen, and also please feel free to visit our lab website at packages.unr.edu/June. Thank you.